Welcome to your first Vodcast of the year. Vodcasts are like lectures or tutorial videos that you watch at home. In class, we will build off of the information that we learn here. To be prepared to watch a vodcast, you will need the following supplies. First, you will need your yellow lecture outline. If for whatever reason you don't have this, you can find a PDF copy of it on my website. You're also going to need something to write with. On your yellow lecture outline, you'll notice that there are many empty spaces. As you watch the vodcast, you'll fill in these empty blanks. Feel free to take additional notes as you watch. These are notes that you will use throughout your time in chemistry. Remember, you have the power. As you watch the vodcast, you can pause, rewind, and replay as you need to. So let's get started. We use chemistry to answer questions about things that we see in the world. For example, if we look at the match at the right or think about a burning candle, we might come up with some questions like the ones listed here. You might notice that when something burns, the amount of stuff left over seems to be smaller than what we started with. You might ask how you account for that change or where the original matter was lost. Asking these sorts of questions is an integral part of chemistry and science as a whole. To study the process by which we answer questions like those posed in the last slide, we are going to study two unrelated chemicals and their interaction. This interaction led to the serious environmental issue, depletion of the ozone layer. There is a layer of ozone present in our atmosphere. This layer protects us and our skin from the impacts of ultraviolet light. You can see in this picture that these students are further protecting themselves from this harmful type of solar radiation through the use of sunscreen. In the 1970s, scientists began to notice a decrease in the concentration of ozone in our atmosphere. This was worrisome because ozone protects us from UV radiation. Notice this note is outlined in yellow. This is an indication that you should fill this information in on your lecture outline. UV radiation is dangerous because it causes molecular level changes in our skin cells, which result in cancer. Just like UV radiation damages our exterior layer, our skin, it also causes harm to plants, which can have a ripple effect up the food chain. Let's start by taking a look at ozone. The ozone molecule is made up of 3 oxygen atoms bound together. Each red ball in this image represents an oxygen. The line between them represents their bonds. The ozone molecules hang out in a relatively thin layer of the stratosphere. The ozone layer is thickest near the equator and thinner at the poles. This means that as ozone was depleted in our atmosphere, its reduced concentrations was most noticeable in places closer to the poles, like for example Australia or Antarctica. Here's another illustration of our atmosphere. You can see that we live in the troposphere. And the ozone layer is located just above the stratosphere. That layer of ozone is going to serve as a protective barrier to both UVB and C types of radiation. If those wavelengths of light were able to pass through our atmosphere, life as we know it would probably not exist here on Earth. Let's take a look at how ozone is formed. Ozone, O3, is formed when UV light hits an oxygen molecule, which is an O2. This breaks the bonds in the O2, causing it to break into 2 independent oxygen atoms. And you can see that in the diagram at the right there. One of these atoms joins another oxygen molecule, that's the O2, and that forms ozone. The ozone molecule, once it's formed, can also reabsorb UV radiation and use that energy to break up into an oxygen atom and an O2 molecule. This is basically the reverse of the reaction that you see above. By absorbing the UV radiation to either form or break down the ozone layer prevents that radiation from reaching the Earth's surface. Chlorofluorocarbons are the other chemical that we are going to discuss. If you look at the diagram at the right, you can see that the chlorofluorocarbons are made up of a central carbon atom, that's shown in black, that is bonded to some chlorine atoms shown in green. That's also where the chloro part of the chlorofluorocarbon comes from, and at least one fluorine atom, and that's shown in blue here, and that's where the fluoro part of the name comes from. Chlorofluorocarbons are no longer used today, but they used to be a common component of refrigerators, foams, and propellants in spray cans like hairspray, bug spray, or shaving cream. When you spray one of these products, the CFCs present in the propellant are released into the air. This is a problem because CFCs are stable. This means that it takes a long time for them to break down. What scientists began to observe was that as the concentration of CFCs detected in the atmosphere increased, the level of ozone decreased. So scientists began to believe that there might be a connection between these two chemicals. So we're going to pause here. We're going to come back to this problem in a little bit, but first we're going to discuss chemistry and matter. So let's start with some definitions. Matter, which you've probably heard of before, is anything that has mass and also occupies space. In other words, it has a volume to it. Anything that doesn't fit this definition, anything that isn't matter, is defined as energy. Both matter and energy are conserved. This means that they don't just disappear. This is what Albert Einstein's famous equation, E equals mc squared, shows us. It shows us that matter and energy can interconvert. Further, it shows that a small amount of matter can be converted into a large amount of energy. This is what we see in nuclear reactions, not something we do in a chemistry lab here at school. Let's go back to the components of the matter definition. One component was that matter must have volume. Volume is how much space something takes up. To measure the volume of a liquid, we use the tool at the right, a graduated cylinder. To read the volume on a graduated cylinder, we look at the level where the liquid is. However, what you'll notice is that the liquid doesn't make a straight line across the graduated cylinder. The top of the liquid is actually slightly curved. This curvature is called the meniscus. When reading the volume, we want to look at the bottom of the meniscus and take the volume measurement from that point. One thing to note about volume is that it can change with temperature. Take, for example, the thermometer on the left. As the temperature changes, that red line, the alcohol within the thermometer, is going to expand or contract, changing its volume. You'll see this change in the volume as the red line moving up or down that glass tube. That changes the temperature volume that we read on the thermometer. That means that when we take a volume measurement, we always need to take into account the temperature of the liquid. Now let's focus on the other component of the matter definition. We've talked about volume, now let's talk about mass. First, however, it's important to distinguish between weight and mass. So let's think about this astronaut who's hanging out on the moon. Do you think his weight is more, less, or the same on the moon as it is when he's here on Earth? If you answered that he weighs less, you're correct. Now let's look at why this is true. This is because mass and weight are different. It's easy to get confused here because in day-to-day language we often use the word weight when we really mean mass. Weight is a function of the Earth pulling down on us. This means the farther you get from the center of the Earth, the less you weigh. The more exact definition of weight is that it is the force of gravity between two objects. This means that it's not a reliable measurement because as distance changes, weight changes. Let's go back to our astronaut and consider another question. How do you think his mass changes when he goes to the moon? As you've probably already deduced, the astronaut's mass doesn't change. This is because mass is not impacted by the force of attraction of other objects. Therefore, we want to use mass of an object instead of its weight. Mass is defined as the quantity of matter in an object. We also have the physics definition written here, but we're going to focus on the chemistry definition. So thinking back to our astronaut, the amount of matter, the stuff that he contained in his body, didn't change as he traveled from the Earth to the Moon. This means that his mass stayed the same when he was on Earth, during his space travel, and when he landed on the Moon. His weight, on the other hand, decreased because the attraction between the Moon and the astronaut was less than the attraction between the astronaut and the Earth. This is why mass is a more reliable measurement than weight. It's not changed by location or temperature. We measure mass in grams or kilograms using a balance, like the one pictured at the right. Matter is studied by many different types of chemists. On your lecture outline, in the table at the bottom of the first page, fill in the type of chemist or branch of chemistry that goes with the description. Inorganic chemists study small molecules that do not contain carbon, like water or oxygen. This is going to be the type of chemistry that we mainly focus on in this class. Generally, we will be working with and exploring small molecules. We will be doing one lab this year that deals with organic chemistry, the next branch of chemistry we will discuss. Organic chemists focus on carbon-containing molecules. Many of these molecules, like the one pictured, have carbon chains or rings which make them much larger than inorganic molecules. Other side groups attach to these rings or chains. The next branch of chemistry we have here is physical chemistry. Physical chemists look at how changes in matter and energy are related. This is, in my opinion, one of the most difficult branches of chemistry to study because it focuses on the quantum level physics that go on within a molecule. This is not something we're going to need to worry about here. It's more of a college level thing. Analytical chemistry is a branch of chemistry where we take what we know about chemicals and their properties and use that information to look at the components and composition of different substances. Analytical chemists get to use machines like GC mass specs, inductively coupled plasma emission spectrometers, X-ray fluorescence, and work in industries that deal with water, soil quality, health, or forensics, for example. The last branch of chemistry that we have here is biochemistry. This is my personal favorite and is what I studied in college. Like the name implies, biochemistry links biology and chemistry. It is the use of chemistry to study living things and their processes. One example of a process that a biochemist might study is the function of iron metals and hemoglobin and how the presence of that metal allows oxygen to be transported throughout the body. I think that this is where we're going to stop. At this point, you should have completed the first page of your lecture outline. We'll continue next time with a discussion of the scientific method and get back to the connection between the CFCs, the chlorofluorocarbons, and the ozone layer.